I'll give you a lecture on tensors and piezoelectricity. It's not a scientific lecture at all. It's just a lecture to explain how works symmetry, tensors, and so on. So the plan is first, I'll come back to the symmetry. I'll explain what is the symmetry, how we describe the symmetry of a crystal or material. And then I'll talk about the relationship between symmetry and physical properties. So we will talk about then, in that case, we'll talk about tensors. So we talk about the second rank tensors, third, fourth, first rank tensors, okay, and different properties which are described by these tensors. Yeah, and then at the end I'll talk a little bit this particular case ferroelectrics, and if I have a time today, if not tomorrow, I'll talk about equilibrium and relationship between different properties. Yeah. So I would like to use, oh, I see already 20 people. It's a good percentage. To see what your opinion on the questions, because you are many, so I cannot ask each of you what you think and so on. So I want to do some exercises together with you. So that's why I would like to use this application to get your answers on some particular questions. So yeah. Okay, so I see that majority is okay. Even it presents 25% or 30% of people in the room. Oh, it's increasing the number. Okay. So, okay, 4 persons are not okay, but anyway, never mind. Okay, so let's start. And the first part, as I said, it will be a symmetry. We're going to talk about the crystals and the symmetry. So it's very important, because what is said, it was said already in the beginning of 17th century, whereas the matter, there is a geometry, and this geometry can be described by symmetry. So it means that all the properties, finally, of the materials, we can describe by knowing the symmetry. And all my lectures will be dedicated to this, to show you how symmetry relates to the properties, how properties are dependent on a symmetry, and you'll see that we can see many things, right? So all the crystalline materials which you know, you probably saw in the museums and so on, the single crystals, most of you saw, and all the crystals have very specific shapes, okay? Quartz crystal has very long shapes usually, and pyrite has, and so on. The snowflakes has very hexagonal, let's say, structure, like 6-order structure. So if you look in details, you will see repeating things, and the branes and the angles are very precise. So it's nothing accidental, even in the snowflake. Everything is very well arranged, and is not something disordered. So crystalline materials are always very ordered. And then later on, in 1665, Hooke said that, observing by the single crystals, he had an idea saying that we should be able to have a small object inside, and then they're just putting many times to reproduce the shapes. So it came the idea that it should be some small atoms or something like this, which brings you. So, and then they tried to cleave the crystals later on, and we observed that the angles were repeating each time, and they came to the idea that it should be some sort of repeating objects, which makes that you can reproduce. So it means you can divide to smaller and smaller and smaller, and you can still get the same angles, the same properties, and so on. So there is some object which is repeating until we get a big object, but you can reproduce this big object from the small ones. Yeah, so how we came, actually, that in the single crystals, the symmetry or the geometrical shape of the crystal is dependent on atomic structure, on the symmetry of a crystal. Okay, so it's the shape of a crystal, the macroscopic shape, is defined by internal arrangement of the atoms and the symmetry. And this makes that we have very specific shapes, and geologists were able to say many things just from the shapes, from the angles, and so on about the single crystals. Yeah. So let's go to symmetry operations. So symmetry operation, it's an operation in which if we transform an object, any object, single crystal, whatever, atoms, if we use this operation, then afterwards we cannot say that the object was transformed. I mean, if you close eyes, I turn the table, which is rectangular, 180 degrees, you open eyes. If you don't know that I did it, you cannot say that I turned it. So this is the idea of a symmetry, how we describe symmetry. If I turn this hexagon by 60 degrees, you will find the same hexagon, right? And you cannot say that I did it, except if I said, oh, you saw that I did it. But if no, you have no proof that I did it, right? Okay, so this is a symmetry operation. It means it's operation which I'm doing, and then I found exactly in the same position, in the same way the object was before. So then we have different symmetry elements, so symmetry operations, so we choose, for example, rotational axis. So rotational axis, we have two-fold axis, so it means we rotate the object 180 degrees around some axis. Okay. Then we have six-fold axis, so we rotate by 60 degrees. So the number of folds, we count 360 divided by some number, right? So two-fold, 360 divided by 2, six-fold by 6, four-fold, it will be by 4, so it's 90-degree rotation, three-fold, 120. So in the nature, in the standard crystals, we don't have a symmetry 5- and 7-fold axis, except in quasi-crystals, right? But it's more complex structure, right? But in standard crystals, we don't have this symmetry, because this symmetry do not to fill up the space in a dense way. Because if you take in a football ball, you need to add some pentagons to do you complete with hexagon and pentagon to complete all the space. So in single crystal, it's a dense matter, so it would have some holes if you use 5- or 7-fold axis. But in real life and in living features, these symmetries, they exist. Like starfish, we have 5 symmetry and so on, but not in crystals. Okay, then another symmetry operation which is very important is the mirror. This is still the rotational axis. So this is just the illustration. For example, if you look at the hand, if you rotate 180, so it's how it looks. So we still, rotational symmetry, it doesn't change our chirality. If I turn my right hand, it's still right hand, which is in different position, right? And if we go now to the mirror plane, okay, some people may mix. What is the difference between two-fold axis and the mirror? When I do a mirror, my right hand turns to my left hand. Okay, when I do rotation, my right hand, this one. Right hand turns to the right hand, just rotate it on the other side, not left. Okay, so mirror, I change my chirality, I go from left to right, and then I do rotation. So if I turn my left, I still have my left hand, I just rotate it. Okay, so this is the difference. Yeah, then we can find many. So when we have, for example, enantiomers, then we can separate like how light is rotating to which side. We can say if it's left-handed or right-handed. Okay, so all the symmetry, when we describe a single crystal, we describe or a structure or any object actually, when we describe a symmetry, we always use one point in a common, like an origin. Okay, so if my object, for example, this hexagon, has several symmetry elements, like two-fold axis, which goes like this, and then on diagonals, two-fold axis, and then we have six-fold axis, which is going through the center in this way, right? It's six-fold, and then we have a mirror plane. You see all of these symmetry elements, we're sharing one common point. Okay, so we always have some origin, and when we defined all the symmetry of the object, but all the elements should share this one point with one origin. Okay, so it will allow us to define the structure. So, and the final element, additional one symmetry element, is inversion center. Okay? So inversion center, it's maybe more difficult to imagine, but it's easy to define mathematically. It's your all coordinates of one point, okay, if it's x, y, z, is transformed to minus x minus y minus z. So you have it's like this. This is the center, so you reverse that. Okay. So this is inversion. So it means you go for origin. If your point is here plus z, this is your origin. Your point will go from the origin to the minus z over y. So this is inversion center. And the notation of inversion center is, so we have like, okay, so still in proper rotations, so additional elements. So in proper rotations, it's a combination of symmetry elements already. So we have rotation plus inversion or mirror. And then we come to complicated history point. We have two like notations, and both of them are still used. Okay? We have international notation, which should be modern one, which we should use. Okay? So in this, when we talk about improper rotations, we talk about rotor inversion. So it means if we have, for example, fourfold rotor inversion axis, so it means we rotate 90 degrees and we do inversion. Okay? But in older notation, which is still very, very used, is Schonfle's notation, we use rotor reflection. So it means you rotate 90 degrees and you do mirror. Your point gets here. Okay? So if you repeat, because fourfold axis, you repeat 4 times to get to the same point. So if you repeat this element, this both notations, at the end you will get the same result. I mean, at the end, if you started here, you have 1 point here, then you rotate 90, then you get here. So the final result, it will be the same. Both notations, fourfold, rotor inversion axis. And this axis we note by 4R, complex notation. It's more complicated when we get, well, rotor inversion 1, what we call the symmetry is inversion, so we don't have rotation, it's like 360 rotation, okay, so it's equal inversion. Then two-fold rotor inversion axis is equal to mirror plane, because if you rotate 180 degrees and you do, and it's get to mirror plane. Yeah? And then there is a little bit more confusion on the three-fold rotor inversion, actually is equal 6-fold rotor reflection. And 6-fold rotor inversion is equal to 3-fold rotor reflection. So it's just exchanging with equivalent planes. So for the notation, so identity is 1 or E. For the proper rotations in international system is very easily it's just number, showing how much folds has the rotational axis. So it's 2-fold, 3-fold, 4-fold, and 6-fold. Right? And in Schonfle's notation, we write C for inversion. In Schonfle's is I, inversion, and in international is 1 with bar. Reflection is sigma or M, and rotor inversion is S. In this case, S with number of folds, and in this case, we just have a number with a bar on the top. So when we talk about symmetry element of the object, we need to say about which axis we are rotating. Because I mean, if your rotation, you have rotation axis around X or Y along Z, it's not the same symmetry at all. So we need to precise about which axis we have a symmetry element. So in the case of rotation, so it's quite easy to understand. So we precise the axis, X, Y, and Z. So we just give in the brackets 1, 0, 0 for X, for Y, 0, 1, 0, for Z, 0, 0, 1. And if it's some oblique axis, so then we'll do 1, 1, 0, and so on. Okay? So it's rotation about some axis. So it's easy, we just precise the axis around which we have this rotation. In the case of reflection, we also talk about the axis. We define this reflection plane, but it's the mirror plane is perpendicular to some axis. Okay? So for example, reflection mirror, which is perpendicular to X, we write mirror 1, 0, 0. Or, for example, mirror perpendicular to Z. So the mirror, for example, this is my Z axis, right? And this is your mirror. So this mirror will be M001. Okay. So the plane we define also by axis, but which is perpendicular. Okay. So this is concerning the notation. Okay, it needs to be, okay. Okay, it works. Okay, so let's practice your messages. Okay, so please say me which operations, symmetry operations has this object. Has 4, axis 4m, 3m, 6m, or -3. -3 is bar free, it means rotor inversion. I can try next time don't to show the results, maybe it might be more funny. And to see at the end, because usually it's to be affected by other opinions. Yeah, you can discuss with your neighbors. It's a very good idea. Try to convince your neighbors. Interesting. Good. Okay. So to make things more difficult, okay, there are 2 possible answers, but one is more correct. Okay. So 4 axis, order 4, I really have a difficulty to see it. I cannot explain, but order 4, it's 90 degrees rotation. I don't know how you could see it. Okay. Anyway, so, okay, we see some 60 degrees, 120 degrees rotations, right? So we talk about this axis, right? And we have rotation. Okay, so now order 6. It means we need to rotate and to find the point by rotating 60 degrees, each 60 degrees. So if I take this point, I rotate 60 degrees, I have nothing here, right? There's nothing here. And then I get here, but by rotating 120. So I cannot have 6, order 6 symmetry. So it's not possible answer C. Okay. So I think it was worth to stop a little bit on symmetry because I see that it's still not, it seems so easy, but maybe it's not so easy. Okay, and then if we look to 3m and minus 3m, okay, okay, the mirror, we had mirrors, so it was the same for all structures. So the mirrors are like this, okay? If you cut the structure like this, and like this, you get a mirror. It's not a mirror like this, okay? It's a mirror like this, and like this, okay? So this is the mirror. Now it is 3 or minus 3. Okay, if you take 3, you rotate, you get here, and you rotate to get here. So it's okay, and this one is rotating also. So 3 is here, but minus 3 also. Yeah, because if you rotate, you get 120 here, and then inversion here. Okay, so both answers, this one and this one, are okay. But this one is better because this one includes It's more complete, this one. Order free, if you get here, here. Okay, 120. Sorry?
You say this is -3.
Yes.
You assume the blue thing and the red one are the same.
So I mean, blue. Yeah, I assume that it's zero plane here. It's like negative and positive. Okay, because if you take that is plus and minus different property, right? Then we cannot do this. It would be just 3m. Okay, so if we assume that this is equal to this, but this one is negative, this one is positive, okay, then it's okay. But if we say that this red is different from blue, then this one doesn't work. It doesn't work, okay? So then we need to see what is exercise, okay? This is where what is the zero plane, or is red and blue, it means that we have the same, I mean, just plus and minus, okay? So normally this is the representation of 3m. This is a physical property, it's like piezoelectric tensor of 3m point group. Okay, okay, go further. So how we represent these symmetry operations mathematically? We have rotational matrix. Very easy, okay? It's the same, okay, we can represent what we're moving a point from one point to another one, but it would be the same as if you move the coordinate system. So it's the same rotational matrices, right? So we have rotational matrix, which defines how one coordinate, the coordinates of a point changes to other coordinates, okay? So it's very easy. For example, the fourfold axis. So for example, we take this point, which has coordinates x, y, z, right? And we rotate around z axis. So the z is not changing. So we see it was z and got to z, right? There is no change because it's around z. And then your x, see, for example, is plus 5. If we go here, it turns to y, okay? But with minus. So it turns to minus y. And y turns to x. So it's quite easy to describe this rotational matrix, to describe how the symmetry operates. Okay, so each symmetry element, for example, the mirror plane, if I had a point and the mirror plane perpendicular to z, so my point is here with x, y, and z, and then I reflect it to the bottom, so I will just change z. From plus z, I'll get to minus z. So it's quite easy to describe if this matrix is how the points are changing. Okay, so inversion element, very easy. You just x, y, z transforms to minus x, y, z. Okay, diagonal matrix minus 1, minus 1, minus 1. Okay, so we are free to propose an answer. Okay, there is no choices now. You need to write a message. Okay, so which symmetry element is generated by coexisting 2001 axis and the mirror 001? So let's say it is our, okay, this is x and y plane. This is x, I don't know if you can see, oh. It's x and y plane, okay? This is your rotational axis is like this, okay? And my mirror is this plane, okay, here. So if I have a point here, my rotational axis, what will do? It will put a point here, right? So, but we agree that it's plus and plus. If z was plus, so I just rotate over there, okay? So now if I add a mirror, what it will do? I'll get, at the bottom, the point with minus, and here also with minus. Okay, I had 2 points, I add mirror, I got 2 points here. So what it would be the additional element? How I could get from the top point to the bottom point? Inversion. Good. But no way, if you look mathematically, we have, okay, rotational axis. So what is doing? You had here x, y, and z, okay? And in this case, your x becomes minus x, z is not changing, okay, and y, it becomes minus y. Oh, okay. Okay, so it's minus 1, 1. Okay, this is rotational axis. The mirror will be 1, 1, minus 1. Okay, because, I mean, the mirror is just changing z. Right, so I don't change x, y, I just changing z. So the product of it, you'll get minus 1, minus 1, minus 1. Okay. So sometimes it's difficult to see just, by making pictures. But you do a product of the matrices, and mathematically you can see what kind of element you're getting. So usually you it's also a good point. Don't understand. Okay. So do you understand how we describe the matrix symmetry element? And then if you have two symmetry elements, you generate third symmetry element. Okay? So what you need to think when you have several symmetry elements, so these symmetry elements will generate other symmetry elements. Okay? So usually when we describe objects or crystal, it's enough to have main symmetry elements, which helps you to describe complete structure. Okay? And then you may have many others, but it's okay. You don't need. Okay? Okay, so let's go to crystal systems. So all you know that there are 7 crystal systems: triclinic, monoclinic, rhombic, tetragonal, trigonal, hexagonal, and cubic. Okay? 7 different systems. And these crystal systems we classified all the crystals with respect to a symmetry. So triclinic crystals has only identity, it means no symmetry, or inversion center, and no other elements. Okay? Monoclinic crystals has single two-fold axis, or single mirror, okay, or single two-fold and mirror perpendicular to it, but nothing else. Okay? It's very low symmetry, it's quite a symmetric object. Orthorhombic has 3 second order symmetry elements: mirrors or two-fold axis. So at least 3. And these 3 elements, it's along x, y, and z in 3 orthogonal directions. You may have 3 mirrors, you may have 1 two-fold axis and 2 mirrors, you may have two-fold axis, but 3 and perpendicular to each other. Okay, 2 second order axis. Then there is tetragonal system. So tetragonal system needs to have 4-fold axis, so roto-inversion or simple rotational axis, but single one, not 3, not 4. Trigonal, single 3-fold axis or roto-inversion 3-fold axis. Hexagonal, single 6-fold or roto-inversion 6-fold axis. And cubic system, many people think immediately about 4-fold axis along 4 directions. It's not necessary. Not all cubic systems has 4-fold axis. Because from the word cubic, you imagine cube. And cube is 4-fold symmetry immediately. Okay? Not all the crystals cubic systems has 4-fold axis. But all cubic systems has 3 4-fold axis along the diagonals. Okay, so it just gives you illustration because we always have a difficulty to imagine the object which is cubic and without 4-fold, right? So this is an examples, for example. Okay, there is no 4-fold axis in this because you see it's rotated in this way, but you cannot get a 4-fold axis. Okay, so all these, it's very easy. I didn't put a question on this. It's too easy to say to which system always belongs. All of them. Yeah, it's hexagonal. You see immediately all this. This is very easy from this side. Oh, it's 6. Okay, so it's all hexagonal. But these two, it's free, but you have a roto inversion. Okay, so you and you get down, and you get down. So it's roto inversion. 6 level bar. Okay, so this is a common definition, which everyone has familiar with this definition, okay? And we talk about crystal system in many books. You just find this table, okay? Triclinic A not equal B is not equal C, and so on. So it's like lattice parameters, okay? And the angles between lattice parameters. So I'll come back. But this is not necessarily you define by symmetry. The definition is symmetry, not this. This comes out from the symmetry, yeah. But when you do measurements, real measurements like X-ray diffraction and so on, you need to be very careful because sometimes you are in errors. And to see if your A is equal B or no, or you are in errors, because this difference might be very small and your errors may be very. So it depends how precise your measurements, and sometimes you're really not able to say from lattice parameters, yeah. And then I did my postdoc with famous crystallographer, and I'm citing everywhere, Professor Mike Glaser from Oxford. He repeated us I don't know how many times during 1 year, do not estimate this crystal system from lattice parameters. You cannot do this. So yeah, so you need to think about the symmetry and to find what is the symmetry. Yeah, so then we have a different lattices, and there is a huge confusion between hexagonal and rhombohedral, right? Because we have, for example, what Paul talked about, lithium niobate is trigonal material, right? And with trigonal material, usually you would describe with rhombohedral cell, because in trigonal we said, I just come back. In trigonal, we say A is equal, B is equal, C, but same as hexagonal, so it's A is B is equal, no, it's like 120. Right? But for rhombohedral, we go A equal B, C, and then A equal alpha is equal beta and gamma, and is not equal 90 degrees. So it's a cell like this, and the angles is not 90 degrees. So alpha is equal gamma and beta, and it's not 90 degrees. But usually all these materials, we don't use rhombohedral cell. It's not a common way to use. We redefine the cell hexagonal. For trigonal materials, we use hexagonal cell. And there is big confusion. The people very frequently say, oh, it's hexagonal. The cell is hexagonal, the material is hexagonal. No, it doesn't mean that material has 6-fold axis. Material has 3-fold axis. Trigonal has 3-fold axis, but we use hexagonal cell. But it doesn't mean that material has hexagonal symmetry. It has trigonal symmetry. But it's just definition. This is more convenient, more practical to use because when we find at least 2 angles 90 degrees, and when 120, you divide, it's easy to get to orthogonal reference system. It's much easier than in rhombohedral cell. That's why we're using. So another particular thing that we're using, but I'm introducing a little bit too early this in my slide, but we use not 3 indices, Miller indices, HKL. We use 4 indices, but I prefer to come back later. Okay. So we come to the point group. So we had 7 crystal systems, and in each crystal system, we have several point groups. So point group is a group of symmetry elements around one point, because all we need to share one point, one origin, and is able to describe the total symmetry, geometry of an object, right? So we have many different point groups. As you see, for example, in tetragonal, each of them they have main 4-fold axis, in hexagonal 6-fold, trigonal 3-fold axis, and so on. And if you see in the cubic, some they have 4-fold axis, some they have just 3-fold axis, and no 4-fold axis, and so on. And monoclinic just have 2-fold rotational axis, or one mirror, or perpendicular to each other. And orthorhombic also only 2nd order symmetry, right? But we have several elements together, at least 3. Yeah. So we separate to the point groups. And with these point groups, you can describe not only all the crystals, but you also can describe any object around you. Okay, the symmetry of any object you can describe by using these 32 point groups. Okay, so it means that it is, it's the, how to say, the notation is coming for each point group just after I have a table, but it means that it's along, it's defined, the element is defined along the same axis. So in this, in monoclinic, so for example, the two-fold axis is along y, and the mirror is perpendicular to it, along to this axis. So when it's slash, it means it's defined by the same axis. Okay. So in, for example, in this case, it means the four-fold axis is parallel to z, and we have a mirror plane perpendicular to z. So it's defined by the same axis, the element. So for the distribution of a symmetry in the nature, so we have inorganic crystals and organic crystals. Yeah? So you may think, I don't know, but nature is very symmetric, probably, what you would think, but not really. Not really. If you look at cubic systems, okay, M3M is quite popular one, okay. But when you look others like tetragonal, hexagonal, it's quite small percentages, and the biggest one is monoclinic. It's 44, almost 45% of all inorganic crystals is in this group, 2/m, monoclinic. So it's quite non-symmetric nature. It's not really symmetric, but all others were quite rare. Okay, so we see clearly that, and really like monoclinic, triclinic, yeah, we have 40%, 14%. So it's really non-symmetric. We have very low symmetry in the crystals, actually. But we have some popular cubic systems. Yeah, but they're more used. Because usually we imagine the crystals around us, what we're using. But if you look at all the systems, the distribution is quite different. Okay, so if we go to the order of the CMOS, which was your question. So actually it's not so simple, but it's very important to know this part, because when we're going to talk about the tensors and definition of physical properties, we are defined according to these rules as a point groups. Because in definition of the physical properties, it will be the second part of my lecture, we use the tensors. All the physical properties are described by tensors, right? And in the tensors, we use a reference system. And the tensors are defined to the point groups. And the point groups for each crystal system has different notation and reference system. So why make simple if you can do complicated? Okay. So, well, in triclinic it's very easy because it's just a point symmetry. Okay, nothing to do. In monoclinic, you already have two possible settings, or you have C-axis unique or B-axis unique. So you need to be sure according which direction they define the symmetry. In orthorhombic, it's easier because we just put the symbols A, B, C, or in other words, X, Y, Z. Okay, so it's easy orthorhombic, like a common orthogonal system, X, Y, Z. Tetragonal, when in case tetragonal, trigonal, and hexagonal, we always put the main higher symmetry axis in the first position. And this first position, it's always C. I mean, the main symmetry axis is defined along C-axis. It's a C-axis. It's a C-axis polarization and so on. It's always C-axis. Okay, so you define your symmetry, the main symmetry along C-axis, perpendicular. And then you have a plane symmetry, which in these cases, in tetragonal, trigonal, and hexagonal, the symmetry makes that A and B, the symmetries are the same. So it means along X and Y is the same. Concerning the slides, they will be available online. So you have all the tables. Okay. Yeah, and then the third position, it's more particular orientations. It's like 1, 1, 0, and so on. Okay, so it's that. And in the case of cubic system, so the first is symbol, it's A, B, or C, so it's in other words X, Y, or Z axis. So it might be four-fold or two-fold axis. Then in a cubic system, three-fold axis is always diagonals. So it's always 1, 1, 1 orientation, what we call, okay? So we have 4, 1, 1, 1 orientation, so 4 three-fold axis. So it's always in the second position. It might be in the first position if we don't have at all four-fold or two-fold axis, but usually we have. Okay, and then we have the third position is 1, 1, 0 orientation. Yeah. So a little bit of practice. A point group of a subject, please. Easy. Just think what kind of elements you have, and then try to find. Probably you should first think which crystal system it is. Okay. And then try to guess. It will be easiest way. I should ask what it was a point group. I should leave, like a free choice. Someone seeing the symmetry. Nothing symmetric inside. It's very funny because some of in the room they already followed these lectures. So it's repeating.
So, why you have always highlighted some of the...
Because I'm reproducing the same table. It's just a question of time. Do you delete or no on your image if you had the underline for one stuff, and then you just underline the yellow ones, it's centrosymmetric. We have inversion center inside. Okay? So if you want the meaning, but you always see you have a mirror and rotational axis perpendicular to each other, and it makes that you have an inversion center. So all these, yes.
Just explain if you have like a monoclinic, what is the two axes and one mirror. And
so monoclinic is, as you say, you have three possibilities, or 3 point groups. So it means a point group in which we have only two-fold axis, only, okay, nothing else, just two-fold axis. Another group which is, for example, just a mirror, but not two-fold axis. And the third one, we have two-fold axis and the mirror perpendicular to it. Yes. Yeah, I mean, 2 over m, it means it's along the same axis. Okay, it's defined, for example, z-axis, so it means along z, you have two-fold rotational axis, right? And the mirror perpendicular to it. No, perpendicular. Yeah, because, I mean, when you describe the mirrors, its axis perpendicular to the mirror, not in. Yes. So if this means you have two-fold axis and the mirror perpendicular to it. So the clinic decreasing, good. So it means we start to understand how we define mirror. It's a very important point to understand where is the mirror. Okay. So what is increasing? Okay, monoclinic decreased, because it means if it's this one, so it means we have two-fold axis. Okay, I think everyone saw this two-fold axis that you can rotate. Okay, but there is no mirror perpendicular. So it's not this. It cannot be, but we have some mirrors, right? We have mirror and here and several. Okay. Cubic pre-fold axis, I don't know how you could see threefold axis. It's quite complicated. Tetragonal fourfold axis, so also no. So yeah, so we need to support this group, right? Or rhombic one. So yeah, we have twofold axis like this. Everyone, I think, saw it, right? And then we have mirror, which cuts like this, right? And the mirror like this, okay? Like this and like this, right? So one mirror is perpendicular to X. One mirror is perpendicular to Y, okay? And 2 is along Z. So it is group MM2, okay? Because there is no mirror in the Z, right? And there is no others, but anyway, you clearly see this is Z axis for 2, and then it's X and Y, you have 2 mirrors perpendicular. Okay. So it is orthorhombic. Okay, so you have a table, I will not really comment, but you have a table which I will leave in slides. Okay, so you have both notations, international and Schoenflies notations of the point groups, and then all symmetry elements inside. Okay, so if you want to know what kind of symmetry elements you have in that point group, just go to this table and you will find it. And especially it will be interesting, for example, if you want to check if your material piezoelectric or no, you can go to look for inversion center, right? But I'll come back to it. Okay, so you have all the elements. So until now, what I described, how I take a point, I take an object, and I describe its symmetry according to this point. What is the symmetry of the object, right? We had this, so what we call the point group. So now if I take this point, for example, a chair, and I will distribute it in the same way. Well, it's not very well distributed because it's tilted a little bit, but if I do in lines, right, I will do what we call translational symmetry. So for example, I use the point group to describe this bird, and then I reproduce the same bird many, many, many times. So in the crystals, we do the same. We take some group of atoms, we describe this point symmetry, and then we just reproduce the same thing many, many, many times. Okay? So we have some examples of translational symmetry, how we can reproduce the same. You find a group which you can define, and then you have to be able to reproduce just by simple translation of the object. So for translational symmetry, that's why we describe like primitive or unit cell. So the unit cell, which we're going to describe the symmetry, point symmetry, and then we are going to fill up the space with it. Okay. So this unit cell needs to be described in such a way that it should fill completely, without any openings, the complete space. Okay, so we limit in the shapes which can be like cubes and so on, which helps you to complete the complete space without, so you would not like to choose just triangle, for example, when your symmetry becomes too complicated because you need to rotate and so on. So just choose a shape which you can translate, and then we try to choose the smallest shape possible, because now we have a big choice to put many atoms, few atoms, and so on. So we choose the smallest possible, and with the highest symmetry. So highest symmetry, smallest volume. This is like how we would choose the primitive cell, and then we the space. So when we come to lattices for different crystal systems, we have several different possible. And when we come to triclinic, monoclinic, and we have body-centered, volume-centered, and so on. But all this is already not really important. I'm just showing for your general culture. Because all what I need to describe the physical properties, it was the point groups. Okay, I don't need all this, but I just want you to know. Yeah. Yeah. No. Oh, no. In the lithium niobate, you have a unit cell which contains two units. You have lithium, niobium, O3, so it's twice this. So we have 2 lithium, 2 niobium, and then you need to count the element, but you have two formula in one unit cell. Okay? No, it's not for one element. It's for all the structure. Okay? And so you describe all the structure in this unit. And then you just translate. Okay? Okay. So some more a little bit definitions. So what we call direction in crystallography. So in crystallography, the direction is just like a vector. Okay, so if we say direction 2, 4, 0, so it means component 0, z-axis is 0, and along y we have 4 cells, so 1, 2, 3, 4, because unit cell parameters is A, B, C, so we have like 4B and 2A. Okay, so you get this vector. Okay, so it's a simple like vector definition, and 4 to 0, you get 4A and 2B, and you get this vector. Okay, so this is direction. And direction, we make these squared brackets to get. Right. Then we have Miller indices. We put a simple brackets in parentheses. So this describes the planes.